Hi, my name is Fernando Urdaneta. I'm a lab analyst from the Water Research Center of Zulia University in Venezuela. And this presentation is about the treatment of groundwater for industrial uses. First, as a manner of introduction, I want to speak about the water consumption worldwide. Water demand is heavily influenced by population and economic growth. In 2011, China, India, and the USA had the highest consumption, representing 16%, 13%, and 10% respectively of the worldwide total. Although these were mentioning that economic growth can also lead to relative reduction of per capita consumption. This is due to the development of more efficient technologies. For example, in the same year, 2011, Bolivia had a bigger water consumption than the USA, even though the Bolivian economy is 10 times smaller than the USA. This is due to technological advancement that allows the USA to produce more wealth using less water. This is important because there's a limit to how much water we can consume. For example, only 3% of the global water supply is drinking water. And you have to take into account that within that 3%, it is counted the amount of water that is trapped in form of glaciers and in the poles. So that water is not easily accessible. This has created pressure from, this has led to pressure from both the regulatory bodies and the consumers for more efficient industrial processes, increasing the cost of using water. This is particularly alarming and hurting in the food processing industry, where the use of water is quite intensive. Now, in Venezuela, the situation is particular. The rising costs associated to water aren't linked to the issues mentioned before, but to several endemic issues. The first one is the historical economic dynamic of the country. The discovery of oil and the surge of the pelagic industry led to demographic imbalances. The population is heavily concentrated in the north-occidental coastal areas where the better paying jobs could be found. And even though Venezuela counts with plentiful water reserves, these are far away from the population center, which means the supply of water requires heavy investment in infrastructure. Which led to the next issue. In Venezuela, public services are heavily subsidized and monopolized by the state, all of which disincentivize private capital for investing in the sector, meaning that the Venezuelan water industry is dependent of public investment, which has been very poor for the past decade. This has led to the crumbling infrastructure for example, in 2015, the water consumption in Caracas was 500 liters per person per day. And considering that the recommended consumption by international body is 220 liters per day per capita, you can see that is a high imbalance of water. There's an irrational use of water. But while that was happening here in Maracaibo, where I live, there was, or there is still to this day, water rationing. These imbalances in water distribution is also caused by the central planning of the messy central planning from the state. Also, it's important to mention that in 2015, 5,000 liters per second, that is equal to 30% of the supply to the capital, was lost due to leakage. The outcome of this factor is an unreliable water supply, which has paralyzed the food processing industry in Venezuela. Now, the proposal is a project that was conceived with the idea of presenting an alternative to the municipal water services. Zulia, as where I am located, is a state located in the western part of Venezuela, in the border with Colombia. Is rich with underground water. Around 3,000 underground sources are estimated in the region. Sadly, this resource isn't exploited as it could be by the local food processing industry. The rational use of underground water could lead to new economic opportunities, which will benefit the crisis real estate. Uh, this underground, the underground source that I use for my study is located in San Francisco, which is in the south of the capital, and it's near industrial park. The idea is to design a really simple pre-treatment steps. The simplicity is key due to the limited capital most local companies have for such investment. Also, the economic situation has led to a massive immigration, and it's difficult for local companies to retain personnel. So it is important that the treatment system can be operated with minimum experience and training. That's why the pretreatment proposal consists of simple steps: aeration and disinfection. Um, the initial part of the project was to do a characterization of the underground source. This characterization was carried using the standard methods for the examination of water and wastewater, and then were contrasted with the Venezuelan legislation. Here in the presentation, I just highlight some of the values that I consider more relevant. For example, both color and iron are above the limit allowed by the law. Both are probably related to the are related. The color is probably due to the oxidation of iron. We have to remember this is an underground source. So the moment you extract the water, it gain contact with air. So all the iron start oxidizing and turn to a red color. From the microbial point of view, we can see that the microbial load is really low. The only marker that was detectable was the heterotroph. This group of bacteria is really ample, and not all of them are pathogenic. So only with the presence of this marker, you can assume that the water won't be harmful to the human health. But since it is above the concentration of this bacteria is above the permitted limit by law, disinfection step is necessary. The technique used for aeration was diffuse aeration. 3 flows were tested. Since no significant difference was detected, the lowest flow rate was selected. The graph shown has in the y-axis the measured concentration of real color, apparent color, and turbidity, while the x-axis shows the aeration time. It's important to note that the difference between real color and apparent color is that real color is measured after a process of filtration. So ideally, since we have a aeration process that will oxidize the iron, the real color should be much more lower than the apparent color. Sadly, we didn't observe that in the experiments. This is probably because the aeration didn't oxidize the iron, or the filter used or wasn't able to capture the oxidized iron. Next, we did the disinfection test. The disinfection technique chosen was chemical disinfection using chlorine. This is because chlorine is readily available in the local market, and also it's a really simple method of disinfection. As was noted before, the microbial load of the water was low, although higher than legally allowed. So it was no surprise when the chlorination, after the chlorination, the heterotroph became undetectable. The graph shown is a chlorination curve. The y-axis shows the residual chlorine, while the x-axis shows the amount of chlorine added. This test is useful since it's allowed to determine the amount of chlorine needed to have residual action, also known as breakpoint. This means that there's still enough disinfectant in the water to neutralize any infection that occurs downstream. Set point was at 1.296 milligrams per liter. The conclusion of the project was that the aeration test was not conclusive. The results weren't the ones to be expected. Although we believe that further filtration should bring better results. The bacteria in the water showed to be really sensitive to chlorine. Was destroyed after a few seconds of contact. So disinfection needs to be carried carefully to avoid excess of disinfectant. And due to the concentration of iron, color, turbidity, and nitrate in water, the salt isn't suitable to be used in processes where water is to be in direct contact of the product of direct consumption under the Venezuelan law. So further treatment is required.